Welcome to this Gretl tutorial on time series. In this tutorial, we will be comparing the performance of linear, quadratic, and exponential trends when working with time series data. In this video, we will be working with data on monthly retail sales in the US running from January 1955 to January 1996. This is the data set discussed in Chapter 4 of Diebold's book, Elements of Forecasting. We will use this data and estimate a linear trend, a quadratic trend, and an exponential trend, and finally compare the performance of these trends or models using the root mean squared error. Let's go to Gretl. In Gretl, I have already loaded the dataset in the file retail.gdt, which came in the Gretl data file format. Note that Gretl already knows that this is a monthly time series with a range that goes from January 1955 up to January 1996. And our only variable at this time are the retail sales over this time period. The first thing we may want to do when exploring any time series is to visualize how the data changes over time. For this, we're going to come to View, Graph, Time Series Plot, and I want to plot retail over time. The graph shows several things. First off, it should be clear that this is not a linear trend. We cannot clearly trace a straight line that represents what we're looking in the plot. Rather, it appears that the sales are growing over time in a nonlinear form, which could be either a quadratic form or an exponential form. This video is about assessing which of the two forms, or actually the three forms, better represent what's happening with the data. We also note in the data that there are no clear seasonal factors, in the sense that month over month, retail sales do not appear to vary significantly. We can actually test this by adding dummy variables to all the series of models we're going to be running in this video, and note that the dummy variables do not have statistically significant coefficients, but I'm going to leave that to you. We will only be focusing on the trend in this video. I'm going to close this plot. In order to run a linear model with retail, we need a variable for time. I'm going to add this variable by coming to Add Time Trend. And note that Gretl just created the time variable we can use to regress retail against time. So let's do that. Let's run a linear regression model that has retail as dependent variable and time as the only regressor. I'm going to click OK. This is our first regression output. Note that it has a very high R-square of 89.39%, and that time, as we expected, has a positive and statistically significant coefficient, which implies that the retail sales in fact grow over time. I also want to examine visually the performance of this model. For this, I can come to Graph, Fitted Values against time. Note that in the graph, there are sections where the real values in the red line are above our linear trend. In the center of the data, the real values are below our linear trend, and in the later years, the real values are above our linear trend. We can actually assess this also visually by checking out the residuals. I'm going to come to Graphs, Residual Plot against time. And let me put them one over the other so that we can observe where the residuals early in the data are above 0, they are positive. In the center of the data are below 0 and then back up. This is also an indication that our model is not really performing well in modeling what is happening with the time trend. Let me close these plots and keep this model handy right here. Now let's run a quadratic model. In order to run the quadratic model, in addition to the linear time variable, we need its square term. So we're going to select it and come to Add Squares of Selected Variables. Gretl has now automatically created square time as a variable that we can use in our model. I'm going to now run a new linear regression model that this time not only has time as regressor, but also the square of time. and I click OK. Note that relative to our prior model, our adjusted R² has increased significantly. We have gone up from a prior 89% all the way to a 99%. So this model is certainly performing better. We also note that the square term has a positive and statistically significant coefficient, indicating that we have a convex relationship between the retail sales and time. Let's visualize this. We can come to graphs, fitted versus actual against time, and note that the quadratic trend fits the data almost perfectly. We're going to once again look at the residuals by coming to graphs, residual plot against time. And even though there are sections, in particular at the beginning, where the residuals are negative, which indicate that our model is predicting values above the actual ones, overall it appears in a much regular way relative to our prior approach. So everything seems to indicate that this model is better than the prior one, not only visually, but also based on the very high R²s. I'm going to leave this model here for comparison later. Finally, let's evaluate the exponential trend. In order to run a model with an exponential trend, our dependent variable is no longer going to be retail, but rather logged retail, or more specifically, the natural log of retail. Working with these kind of variables is very customary, so much that Gretl can create the log of the selected variable automatically. So we select retail, click on log of selected variables, and we now have L_retail as the log of retail. So we can use this in a new linear model, which is not going to have retail as dependent variable, but rather log retail, and it's not going to have the square term of time, only time. We are ready to run our model. We click OK, and note that once again we have a positive coefficient for time, but very interestingly our adjusted R² went low. Now there's a very, very important nuance in comparing the R² of this model against the other two models. Remember that the R² explains how well do the independent variables explain the variance in the dependent variable. But the dependent variable in this new model is not the same one as in the prior ones. So they are not comparable. I repeat, we cannot compare the R² of this model since this model has log retail as dependent variable, while the others have retail as dependent variables. Following what we did with the other models, let's examine this visually. I am going to graph the fitted and the actual values against time. But note that this looks like a straight line, which is not what we had before. The real values plotted in this case are not retail, but rather log retail. We can also visualize the residuals plot by coming to graphs, residual plot against time, and it goes up and down around 0, which makes us cast some doubt on the performance of this model, yet we still have no clear criteria to decide if this is a good model or not. I'm going to close these plots. Okay. Now we have three models, but we are unsure on which of the three performs best. And the way we're going to compare their performance is in comparing how well are they able to forecast the actual values observed in the data. So I'm going to go model by model and run forecasts such that we can then compare the predicted values to the actual ones and compute the root mean squared error. Let's start with the linear model. I'm going to come to Analysis, Forecasts. And Gretl is warning me that there are no values in the data for which we did not observe the actual values, meaning that we're not making any out-of-sample prediction, which is exactly what we're trying to do. So we can ignore this prompt. I'm going to run the forecast for the entire time span of the data. So I simply click OK. And Gretl is now showing us the real retail value for each month this prediction and the usual standard errors in 95% confidence intervals. In this case, all what I am interested in is the prediction, which I'm going to store as a new variable in the data. I click this plus sign, and I'm going to call this prediction of retail linear. And the description, just so we don't forget it, is the prediction of retail using linear model. And we have saved that in our data. We can now close this window along with the corresponding plot. And let's do the same for the quadratic model. We will come to Analysis, Forecasts, ignore the prompt, run the forecast, and store the prediction. And in this case, I'm going to call it predicted retail of quadratic. Correspondingly, the description is going to be forecast of retail using quadratic model. And we can close this. Finally, let's create the predicted values for the exponential one. However, note that we will be creating forecasts for log retail, but we will get to this in just a second. We come to Analysis, Forecast, ignore the prompt, run the forecast, and save it. Now this one is not a prediction for retail. This is a prediction for log retail using the exponential model. And I'm going to close the output and the corresponding plot. So now we have three variables with the different predictions. But let's look at the descriptive statistics of these to note if it makes sense to use the forecast of log sales using the exponential model. If we look at the summary statistics, note that the mean values of retail using the linear and quadratic models are in the order of 67,000, while the predicted value for the log retail is 10.78. It doesn't make any sense whatsoever. We also have similar discrepancies in the standard deviations that represent the volatility of the data. We're simply dealing with different units. So we must now convert the log retail to a real retail, and we're going to do this by adding a new variable which we're going to call predicted retail using the exponential model. And as we discussed in class, the way we convert this is by computing the exponential form of the logged value. And we click OK. So note that predicted retail using exponential is the exponent of predicted logged retail using the exponential. Let's quickly compare the summary statistics and note that now they are all in the same ballpark. 67,000 for the linear and quadratic models, and 66, almost 67,000 also for the exponential one. So now our predictions are all in the same units. The following step is going to be to take all these three predictions along with the actual retail value to Excel. I'm going to export this data set as a CSV file, and I want to export real retail, the predicted one from the linear one, predicted from the quadratic one, and predicted from the exponential one. Note that I'm selecting retail, not logged retail. I'm going to click OK, comma separated values, and simply store this in my desktop. This is what we observe when we open the exported CSV file in Excel. We have an identifier of the observation, the real retail value, and the three predictions we exported along with it. I'm going to just quickly reformat this for legibility purposes. There we go. Okay, so the first thing we want to compute is the squared errors or the squared differences between the actual and the predicted values. And I'm going to be doing this for each of the three models. So let's start with the squared error of the linear model. The error is going to be the difference between retail, and in this case I'm going to lock my column so I can drag my formula, minus the predicted one squared. Okay? It is a very large number, but we're not going to worry about that. If I drag this all the way to the bottom, such that I compute the squared error for all of my observations, I can now compute the root mean squared error for the linear model. What I'm talking about is the square root of the average squared error, which is what we have here. I'm going to select all this range of values, and I have my formula. Okay? Let's do that for the next model. I'm going to call this squared error of quadratic. I drag the formula, so now that I have the difference between the predicted retail from the quadratic model and retail squared, and I'm going to have this for all my observations, and my RMSE for the quadratic model is going to be much lower than the one we had for the linear model. Note once again, this is taking the average of the squared errors and then its square root. And let's finally do this for the exponential model. Where now we have a root mean squared error of 5,483. So based on this metric, what we have discovered is that overall the quadratic model is fitting our data better. If we compute the deviations from the predicted values to the actual values, we square them. We take the average of all those squared errors and then take the square root of that average. We find that the quadratic model has a root mean squared error of 2,763, and since it has the lowest error of all three models, this is our best model. Now, we might be able to avoid some of this work by working in Gretl. So let's quickly go back to Gretl to conclude this video. Here in Gretl, even though we will not be able to do all what we did in Excel, we can certainly do enough to assess the quality of the model that may save us the work of exporting data to Excel. What we're going to do is compute the squared errors and then compare which of the three models has the lowest average squared errors. So to compute each of the squared errors, what we're going to do is to create a new variable, which I'm going to call squared error of the linear model, which is going to be equal to retail minus the predicted retail from the linear model squared. I click enter, and I'm going to create the squared errors of the other two models. So I come to add, new variable, squared error of the quadratic form, which similar to the one before is going to be equal to retail minus the predicted retail from the quadratic squared. And we finally create the variable for the exponential model, So we come to add new variable, squared error of exponential, which is equivalent to retail minus, and note that I will select the predicted retail of exponential, not log retail, also squared. And if I now compare the descriptive statistics of these three squared errors, we note the following. The squared error of the linear term is the largest, since it is a certain number multiplied by 10 to the power of 8. Following it, we have the squared error of the exponential one, since its mean value is 3.0 times 10 to the power of 7. And the smallest one is the quadratic one, with a mean squared error which is only multiplied by 10 to the 6. These numbers are much greater than the ones we had before, mainly because we have not taken the square roots of these errors. However, if a number is larger than another, so will its square root. So, in determining which one has the smallest error, we can use this metric rather than the root of it to determine which is our best model. With this, we conclude this video. Thank you very much.